We are beginning a new unit today, and this unit is really kind of more the foundations and building blocks that we're going to be using throughout the course of this class. There will be things that we learn in this unit that we will talk about and use in May. Okay, so there are key foundational concepts that we're going to move forward through with this, and so we're going to start this introduction today. Now, I do want to say something in preference. We just got done with this surface area and volume three-dimensional unit, but if you recall, we started that unit off talking about some of the basics of geometry: point, line, plane. We talked about the difference between lines, line segments, and rays, right? So like the difference between a line is that a line extends in both directions infinitely, right? While a ray has a clear endpoint and it extends in one direction, and then a segment has two clear endpoints, right? And so we're going to use a lot of that language from that very first lesson. In fact, that lesson really more applies to here and going forward, but I put it right before the 3D unit so that I can talk about things like planes and points and collinear and non-collinear and coplanar and non-coplanar so that you are familiar with some of the language that we start speaking in this class. But today, it's going to get even deeper in the language. And so you're going to have good listening skills and good interpreting skills as we work through this, okay? So let's just kind of keep that in mind. So today we're going to be talking about measuring segments, right? These are our straight paths. Again, we're mostly working with straight paths here, and we're referring to these straight paths with a clear beginning and a clear ending. And so if we wanted to measure a segment, like you can see I have a segment here, right? And I can count on this line segment 1, 2, 3, 4 right here. Well, if we want to measure a segment, right, this is the distance between 2 points. And we refer to that as the length, right? This is a one-dimensional measurement. The length of segment AB. The length of segment AB. Now, I could write that phrase. In fact, here, let's put this in quotes. I could take this whole phrase and sum it up by writing that. Notice the difference between this and this. What's different about them? Yeah, there's no line across the top of this one. And that is an important difference when you're writing your geometry. This is the difference between something we're going to talk about called number language versus figure language, okay? And the idea is when you see this, you read that statement as the distance or length of the given figure, the given segment AB. So in this case right here, the length of AB is equal to 1, 2, 3, 4 units long, whatever unit we had, like centimeters or kilometers or inches or whatever, okay? Now, here we have two segments. We have segment AB and we have segment CD. And you can see that AB is 1, 2, 3, 4 units long and CD is 1, 2, 3, 4 units long. And so if we made this statement right here, the length of segment AB is equal to the length of segment CD, then the language we would use for that is this word right here. Now, we've used this word a little bit. You've seen this word before in the past, but this idea of congruent means having the same measure, all right? So let's write that down here, having the same measure. And I'm going to do some highlighting here and there. And so if you want to have a highlighter out or a color it out or something, you can do that as well. You don't have to, okay? Now, catch this. The length of segment AB is equal to the length of segment CD. So if those two segments are congruent, then we would write that like this. Now, you saw I had this little symbol here, right? I'm going to draw a little arrow. I'm going to rewrite that symbol. This is our congruent symbol here. It's an equal sign with a little squiggle on top of it. And this is used to say two figures are exactly the same. This is used to say two values are equal to each other. So let's clarify that just a little bit, okay? So let's put a little star here like that. And then we're going to kind of swoop an arrow down here into this space on our notes. And the first thing that we're going to start with is something that I call figure language. Okay, so figure language. Figure language would look like this. The figure, segment AB, is congruent to the figure, segment CD. Or another way we can say that is segment AB and segment CD are exactly the same. Segment AB and segment CD are exactly the same. In every way, shape, and form, the measurements of segment AB and CD are the same. Now, I'm going to use this language as we continue to move through the class. This idea of things being congruent are like identical twins. Every part of identical twins down to their DNA are the same. That's what we talk about when we talk about congruent. Now, that's figure language. Let's talk about number language. So number language is going to look like this. This is the length of AB is equal to the length of CD. So you'll notice in figure language, I use a congruent sign. In number language, I use an equal sign. Okay? And the way that reads is how I just said it. So the length of AB is equal to the length of CD. Now, what I want you to understand, I'm going to circle this little AB here and swoop an arrow over here, is that this is kind of like a variable. In other words, it can be replaced with a number. See, we say numerical values are equal to each other. We don't say shapes are equal to each other. We say numerical values are equal to each other. Okay, equals a math symbol, right? We can't do math with shapes, but we can do math with numbers. And so that's why we need the difference between figure language and number language. Now, it kind of depends on what math class you're in and how much of a stickler figure language versus number language is. If there are certain like proofs, things that you have to write out, evidence for things, like on IXL is an example of one of them. If you don't use the right reason to switch between figure language and number language, do your work and then switch from number language back to figure language, you will actually get that question wrong. Okay? Now, that's a super stickler level of that. We will be middle of the roadish, but I lean a little bit more towards stickler because I do want to make sure to emphasize that there is a difference between this and this. One of them refers to these two objects are the same. One of them refers to these numerical values. Now, it may seem kind of redundant in the sense of looking at something as simple as a line segment. But when we get to triangles, which we're going to do a lot of work with triangles this year, when we get to triangles and we say this triangle is congruent to that triangle, we're saying they're identical twins. Every part in every way, shape, and form are identical to each other. But if I wanted to state all the things that were equal about that triangle, I would have to say this side is equal to that side, and the other side is equal to this side, and the third side is equal to the third side, and this angle is equal to that angle, and this angle is equal to that angle. I'd have to write out a whole lot more. But when I say this whole figure is exactly the same as this whole figure, we understand that that means all of the components of it, right down to its DNA, are 100% the same. That's what we mean when we talk about congruent. That's the difference between congruent and equal. Okay? Questions? Everything okay so far? Pretty good? Okay, now, one of the things that I'm going to do a lot this semester is I'm going to talk about your geometry tool belt or your geometry toolkit. Okay? And this is this idea of what tool are you using to do a problem? Now, I told you that this class is a little bit different than your previous math classes, right? Your previous math classes was, here's a problem, solve it. Here's a problem, solve it. Here's a problem, solve it. Now it's going to be, here's a situation, you come up with the problem and tell me what reason you created your problem that way for, and then you solve it. See the difference? The difference is that you're going to have to write the math problem and tell me why you chose to write it that particular way, and then solve it. All right? So let's talk about the first tool that we're going to put in our tool belt right here. I want you to box this in or highlight this right here. So this is one of our new tools. We had a bunch of tools with our 3D geometry, our surface area tools, our volume tools. Well, now we have something called the segment addition postulate tool. Okay, so here's how the segment addition postulate tool reads. It says if A, B, and C, wait, what do I mean when I say capital A, capital B, and capital C? Yeah, we're talking about points in space somewhere labeled with an A, labeled with a B, labeled with a C. Now, if those points are collinear, what do I mean by collinear? What do I mean by collinear? No, they're not equal, not congruent, because they wouldn't have, because points have no measure. They're on the same straight pathway, right? So points A, B, and C are collinear. Here's an example of that right here. So if A, B, and C are collinear, and catch this, B is in between A and C, then we can say something like this. We could say that the length of AB plus the length of BC is equal to the length of AC. Segment addition postulate. This is AB right here. This is BC right here. How many pens long is AB? How many pens long is BC? Okay. The length of AB plus the length of BC equals the length of AC. How many pens long? That's segment addition postulate right there. Get it? We take two segments, we combine them together, and we get the total amount. All right, now I'll farkify this for you just a little bit. Yeah, that's my little way of doing things. Okay, so I like to think of this like this. This is part plus part equals whole. Or we could do it over here too on the algebra side of things. We could say part plus part equals whole. Part plus part equals whole. Now this is part plus part equals whole for line segments. We're going to have other parts plus parts equals wholes. But this is part plus part equals whole for line segments, and that's what we call the segment addition postulate. This is what it looks like right here. Okay, get the idea? All right, let's do a little work with this, okay? So here we're going to use this diagram. We've got three collinear points, okay? Q is obviously positioned in between P and R, okay? And we're going to find some information here, so we're going to use some numbers. Here's what I want you to do. For this first question, you can see that PQ is 9, QR is 28, and we're going to try to come up with PR, but we're not going to try to come up, we're not going to just try to come up with the answer. We're going to first write a math problem, an algebra problem, an equation, like a segment addition problem, to solve for this question. And what we're going to do is we're going to define PR as X. So we'll say PR, the length of PR, we'll use X as our variable. Okay? Here's what I want you to do. Right here, I want you to write me a segment addition math problem using these numbers and the X. Write me a math problem that's going to find me the value of PR. You're going to write me a problem first before you find me the value. Okay? Go ahead. Give it a try. You're going to write me a problem before you find me a value. Go ahead. I wanted to see from you right here. Write me a segment addition problem that helps me find the value of PR. That's what I asked you to do, right? Then once we have that, we can find the value of PR, right? Then this is just our solving here. So then we add our two terms up and we get 37 units is equal to X. Segment addition postulate, right? Part plus part equals whole. You got it? Okay. Number 2, write me a segment addition postulate problem that will help me find the value of PQ, given that QR is 17 units long and PR is 21 units long. Write me a problem. Right here. Who wrote a subtraction problem? Did anybody? Okay. Subtraction problem is wrong. Because it's not segment subtraction postulate, It's segment addition postulate. It is part plus part equals whole. And when you write it like this, just like the Pythagorean theorem, when you write it like this communicates to me in writing that you understand that this is part of a line segment, this is another part of a line segment. I'm combining them together to get the whole line segment. The subtraction comes in the solving, right? Again, just like with the Pythagorean theorem, the subtraction comes in the solving, and then we find that x is equal to 4. Did that make sense? Do you see why it's not written as a subtraction problem? Okay, because this is the segment addition postulate. Questions? Let's take it up then. All right, here's what we're going to do, okay? We'll do number 3 here. What I would like you to do, and I want you to do it kind of over in this space on your paper right here. I want you to write me a math problem that's going to help me find the value of x if segment EF is 8 times x minus 17 units long, and segment FG is 5 times x minus 3 units long, and EG is 71 units long. Write me a segment addition postulate problem. Okay, go ahead. All right, let's start with this and see if you got it right. This is what you should have put on your paper. Now, I did not ask you to write this yet, but I'm going to ask you to write it now, okay? Because what you're going to start doing is telling me why you chose to set this problem up where you took this expression and added it to this expression and set it equal to this value here. You did that because you were using segment addition postulate. Now, that's the only tool we have right now, but we're going to have another one today, and by the end of the semester, we're going to have about 20. And so you're going to have to know which tool to use at what time, and you're going to have to tell me what's your reason for choosing to set up the problem the way you did. That's something you will be graded on. That's part of geometry. Can you provide me the right reason of why you did it, and can you set it up correctly? And then you got to do the math right, okay? So go ahead, finish this one up. Let's see what you can do. Go ahead. Up with x equals 7. Yes? How many people got that right? Let me see. Pretty good. Not bad. Not bad. Not bad. Not bad. Good. Good. Okay. Okay, so from here on out, you are going to tell me why you're setting up the problems the way you do, like this right here. That will be a part of your test. Okay? Identifying the right tool or the right reason why you set the problem up the way you do is part of what I'm grading on your assessment. So make sure you include this part right here. Let's do number 4. Okay? So you're given some information up here. Length of TV is 14 times some number minus 8. We're given some information here. This TU is 9 times the same number, right? Anytime we see a variable in the same math problem, it means the same value, right? And then we know that the distance from U to V is 5 units. Okay. Start with a math problem. Let's see what you can do. Go ahead, give it a try. Okay, you should have started in this direction. Did you set it up like that? And identify your segment addition postulate tool. Good. Then finish it. Variables on both sides, and all that. How many got x is equal to, how many get 3 for their answer? Yeah? You're wrong. Yeah, wait, how am I wrong? Wait, what? The answer's not 3, it's 29.
Oh, yeah, I got it. Oh, find TU.
Important geometry lesson right there. Answer the question that's being asked, right? So, yes, x is equal to 3. You're partially right, but that's not the entire answer. You were being asked to find the length of TU. And in order to find the length of TU, you need times, and 9 times x plus 2. Got to plug it in here. And yes, I do need to see this work right here, okay? I do need to see that work because I need to know where you got that number from. Make sense? Everybody good there? Make sure you answer the question that's being asked. Okay, here's what I'm going to do. I want you guys to do 5 and 6. I'm gonna let you. What I'm gonna ask you to do is I'm gonna ask you to set up 5 and set up 6 first, and then you can start solving them out. Okay? But because I'm gonna put both setups on the board in a couple seconds here, just to make sure you're setting them up correctly. Make sure you're identifying your tool, setting up your problems correctly, and then you can solve them out. But set up 5 first, set up 6, and then start working them out. And in a couple minutes, I'll put up the setups for 5 and 6 to make sure you're on the right track. If you're still kind of struggling with the problem setup, okay? And if not, then just blow right through. For the setups, make sure you got your problems moving in the right direction for your solving. Check your setups. You should have come up with these 2 answers right here. Yeah? All right, give me a 1 if you got 1 right. Give me a 2 if you got 2 right. Let me see you around the room. Good job. Nice. Way to go. All right, good. Good. Questions? Okay, I want to talk about one other thing real quick. So, is it possible to have a negative answer to this question? No, it is not possible because you can't have a negative length. Okay, like even if we go back up to this first one right here, right? If I started at A and I went 1, 2, 3, 4, that's 4 units long, right? If I started at B and went 1, 2, 3, 4, that's still 4 units long. It's not negative 4 units long. Just because I turned around on the same sidewalk and walked the other direction, it's still 4 steps. If you drive a car and you drive from here to, I don't know, let's say you drive from here to Fresno or to where I live in Visalia, right? It's about 45 miles. You turn around and drive back, you've put 90 miles on your car. Okay, it's not like it goes 45 and then minus 45. So it's not possible to have a distance measurement that is negative. Is it possible to have a negative value for this answer? Yeah, it is possible, right? Because this is just the variable in the problem. And when we plug it in, it could still result in a positive distance here, right? Like, let's just say x happened to be -1 here. Well, we could plug in a -1 here. We'd end up with a +2 value, and that's okay for our distance, okay? So just something to keep in mind in terms of positive and negative. All right, let's flip over and talk about 7 real quick. So take a look at number 7. So let's take a look at number 7. Now, we're not going to do 7 together right now, but let's just take a look at it. So here, you can see in this picture, again, we have 3 collinear points, S, K, and Y, K being in between S and Y. And we're given some information algebraically about the distance between S to K, the distance between K to Y, the distance between S to Y. They're all X-related expressions, right? And now we're asked to find 4 pieces of information over here. So in a question like this, right, you would have to find your X value. And then once you know your X value, you're going to go back and plug it in here, and plug it in here, and plug it in here. And that's going to allow you to figure out these measurements right here. Okay, make sense? So it's just sort of an expansion of what we've done, all right? But there's other things to talk about, all right? Hold on one second. Speaking of that, we're going to talk about a new tool right now. All right, here we go. Right above here, I want you to write definition of, and then we're going to box in that right there. So definition of midpoint. All right, this is a new tool for us. Now we have 2 tools in our tool belt to use for our geometry stuff we're working on right now. Okay? Definition of a midpoint. All right, so let's talk about this. This is going to be an important word for us and an important concept. So, the midpoint of a segment is a point that divides that segment into 2 congruent parts. Okay? So the midpoint of a segment is a point that divides a segment into 2 congruent parts. Now, in this picture, right here, we can tell that B is the midpoint of line segment AC. So here's how we know that. We've kind of talked about these a little bit, but let's be real specific. Draw a circle around that little marky thing. That little marky thing right there. Shoot some arrows down here like this. Those two little what we call hash marks there are congruence marks. Okay? They're congruence marks. And what they tell us is if those marks are the same, 1 hash mark, 2 hash mark, 3 hash mark, something like that, and you'll see more examples of this as we move on. But if they're the same, identical marks indicate equal measure. So congruence marks. On line segments, the congruence marks look like these little hash marks that we cross through our line segments with. We'll have other kinds of congruence marks as well too, okay? But these congruence marks right here indicate equal measure. So when we see this congruence, single congruence mark here and this single congruence mark here, and they're centered in between, we usually write them in between the endpoints of the segment, we're saying that the distance from A to B is the same as the distance from B to C. And if those distances are the same, then that means that they're congruent, which means their lengths are equal. And so we mark that with that congruence, and that means that B must be in the dead middle of AC, because that's the only way you could have 2 equal parts, right? If you take something that's 10 and you split it in half, you get 5 and 5, right? And so that middle comes right in between there, all right? Now, a line, ray, or segment that intersects another segment at its midpoint is said to bisect, it's going to be a huge word for us, the segment, and is called the segment bisector. Now, let's just, again, emphasize this word right here. When a segment, or any figure, any part of a figure for that matter, has been bisected, it has been broken into 2 congruent parts. Okay? Not any 2 parts, 2 congruent parts. That's important to understand. Okay? So in the diagram to the left, okay, B is the midpoint of what? Why don't you should be able to fill in this blank right here. Why don't you write what you think goes in that blank right there? Use correct geometric formatting. B is the midpoint of, you should have written segment AC, right, with the line on the top, because we're talking about figures here. And line what is a segment bisector? Well, here, let's write this in. Segment bisector of AC. Line what? You fill in what you think goes right there. What do you think goes right there in that blank? Line is a segment bisector of AC. Remember, right above, we just said that if a line, ray, or segment intersects another segment at its midpoint, it is the segment bisector. So which line are we talking about here? We're talking about line L. Not line B, not line BL. I can see why you might think I. Legit reason. Okay, but again, lowercase letter and I would have a dot on the top of it, right? Wouldn't be an uppercase letter because it's not a point. So, but good clarifications, right, for us to take in, okay? So this is line L. Again, we can't call it line B because we need 2 points. We can't use L as a point because it's not a capital letter, doesn't have a dot on our graph. So we go with line L. Okay, so we've got congruence marks here, right? So B is clearly the midpoint of segment AC. How do I know that? Because I have a segment bisector in line L, and I have 2 congruent parts from AB to BC. However, up here, it should be pretty clear that K is not the midpoint of segment SY, even though it's in between S and Y. And so if I were to put congruence marks up here, it might look something like that. Great question. Why is there 1 mark between S and K and 2 marks between K and Y? Anybody want to take a gander at that? Gio, what do you think? Because they're not the same length, right? So what we said here was segments that have the same length are going to have identical marks on them. So if I want to indicate that two segments are not the same length, then I need to use differing marks. Make sense? Okay? That's how we know that. And when you see something like this, then you know that K is not the midpoint, even though it's still between. And that distinguishes the difference between points being in between and collinear and being the midpoint or the place of bisection. Well, did you just understand what I just said? Did you get what I just said? Because I was speaking all kinds of geometry. You want to say it again? Okay. All right. What I said was you can tell here that K is not the midpoint of SY because you've got two segments that are different lengths from the congruence marks. However, here, B is clearly the midpoint of segment AC because I have a segment bisector in line L, and that's because A, B, and BC have the same congruence marks on them, making them equal in length. Did you follow it?
Yeah, it's just telling you that.
Yeah. And I used a lot of geometry language to say that. So again, if you fully understood what I said, you're starting to speak my language. If you didn't fully understand what I'm saying, that means that you need language skill work, right? You need to keep polishing your understanding of how I'm going to communicate, because there's obviously going to be more things that I say in this class as we move along. Okay? All right, so then let's take our new tool out for a spin and see what we can do with it, all right? Here we go. If Q is the midpoint of segment PR, find the value of X. I want you to start with, right here, we'll just do it right in this space, and name your tool you're going to use. So write me an algebra problem that would help me find the value of X. Let's start with an algebra problem that will help me find the value of X. Go ahead. And name your tool that you're going to use. This is what you should have done here. Now, this is not segment addition postulate. This is definition of a midpoint, right? We're not given any measures. Notice in the end of the writing up here, there's no mention of measures. We don't know how long anything is. But what we can say is that whatever this value is, it's going to have to be the same as this value. How do I know that? Because Q is the midpoint of segment PR. That means these two distances are the same. I can set those expressions equal to each other. Do you see how recognizing what the question is asking, pulling out the right tool, causes you to set up the problem differently? This is not a segment addition problem. This is setting two expressions equal to each other because you have two congruent segments as defined by this idea of midpoint. Does that make sense? Okay. All right. Go ahead. Finish that one up. Should have gotten X equals 6. Yes? Good? All right. Okay, now I want to show you a different way that I could have written this problem for you. So I want you to write this out here. So I could have asked you the problem here in question 8, or I could have done it like this. So let's put a point right here on your paper, and to the best you can, give yourself a straight pathway like this. And let's put a point here, and let's put a point here, and let's put our letters P and Q and R. And then let's go like this. If I gave you this diagram right here and I said, find the value of X, that's enough information for you to do that. If I gave you this diagram and none of this here and just said, find the value of X, that's enough information in that picture for you to do that. Because these congruence marks tell you that those measures are equal, which means that this expression is equal to this expression. And then you would set them up and solve a problem like this. Definition of a midpoint. Another tool to pull out of your tool belt. Good? All right. Why don't you try to do number 9, set up the problem, name your tool, come down to your answer, do the whole thing. Let's see what you get on number 9. Go ahead. Give it a shot. So you should have done this right here. Definition of a midpoint, your tool, setting two expressions equal to each other, variables on both sides, solving for X. Again, another thing that we did in our lesson 0.1, solving equations, right? The idea was that's where you get good at solving your equations, so that here, all you have to focus on is, am I using the right tool and am I setting up my problem correctly? this part should all be pretty easy to do for you now. This is really kind of the new stuff that we're learning here. What do you think? Not too bad? Okay, let's skip 10. Let's do number 11. 11's a little weird. You've got G being the midpoint of FH. Okay, all right. We got some segments, measurements, 4x plus 3 and 7x minus 12. We know that the whole measure, FH, is 6y minus 2. Find the value of y. Because I said so. No. Okay. Okay, good luck. You did. You should have headed this route here.
That's exactly what I
And we got this again. It's like you did the work and you got the answer.
Okay, now I want to talk about what I have written in blue up here on the screen. Okay. Is this a legit use of the segment addition postulate?
Yes.
Sure, absolutely it is, right? 4x plus 3 plus 7x minus 12 is equal to FH, which is 6y minus 2. The problem is it doesn't help us because we have two different variables in our equation. And if we want to get down to solving, we can only have the one. And so we can't figure out one of those variables with two of them in our problem in just a single equation. We need a systems of equations for that. But we can use our other tool, our definition of midpoint, get a value of x, plug it back in. By the way, that's a great way to check your answer right there. Right? If you're using definition of a midpoint, then you should know that they're the same. If you're using segment addition postulate, whatever you get here and whatever you get here should add up to the total, right? Part plus part equals whole. Okay? And then once you have that value, you can calculate your y. Good? Ready, solid? Okay. Let's talk homework. Let me pass it out. Okay, so again, homework, right? 3, 5, 7, and 8 on the front side. 9, 11, and then 13, 14, 15 on the back side.